Welcome to Parametric Planet. In this video, I would like to talk about how we can optimize the material or the section fabrication process and how we can reduce the material wastage by adjusting our section profiles in the best possible way. For this purpose, I'm using Galapagos Optimization Tool in Grasshopper. And to demonstrate this process, I have created this small script which you guys can follow along. Before dive into the script and run this optimization, I would like to talk about the control parameters which I want to change during the optimization, and also the fitness function which I want to minimize. In this example, I want to move these section profiles both in vertical and horizontal direction, and I also want to rotate these small profiles about their centroid. For this purpose, I have created this gene pool, which is basically the combination of multiple sliders, and each slider control the movement of each profile. If I move this slider, you can see this profile is moving in the horizontal direction. If I move the other slider, the same profile is moving in the vertical direction. In similar way, this profile is rotating about its centroid. The next thing is the fitness function. I have created two fitness functions. One is for the area of this bounding element or the bounding box, and the second one is the collision. With this area fitness function, my goal is to get the minimum area so that I can get the best possible packing among these elements, which ultimately give me the less material wastage, which I am calculating here. And with the collision, I don't want to have any collision among these objects or these profiles, because if there is a collision, then I will get the wrong panel from which I want to cut out these profiles, and ultimately it will also give me a wrong wastage value. The next thing, I'm combining both the fitness function into single fitness function, and the main reason is because the Galapagos only uses single fitness optimization, and that's why I converted these fitness function into single fitness function. Further, you can see that I'm using only 25% of area fitness function, and I'm using 100% of collision. By this way, I'm just creating more influence of this collision fitness function over the area fitness function. You can also change this value. Further, what I'm doing here, I'm adding up these collision values. If this value is 0, it means there is no collision. And if this value is greater than 0, it means there is a collision. And then what I am doing, I'm adding up these values and multiplying this value with the 50 so that I can get a bigger number. And at the end, I want to reduce this number. If this number is bigger, then this optimization tool will try to reduce this one, and it will try to remove if there is any collision here. The first thing I have done is I have created this section profile in the Rhino viewport, and then I have connected these profiles with Grasshopper using the curve, and then I converted those curves into B-rep. The main reason why I converted these curves into B-rep, because if these are just the curves, then these small profiles can come inside this larger profile, and in this case, Grasshopper will not detect any collision if these two profiles do not cross each other. That's why I have converted this one into B-rep. Even if these profiles come inside this larger profile during the optimization, Grasshopper will detect the collision and it will try to move these profiles away from each other. And the next thing, I'm moving this profile using the move component, and I'm getting this vector for the motion through this vector 2-point component, because I'm moving this section profile from original point from their centroid to the next location, which is basically controlled by these gene pools. And this will be the input for the optimization. The optimization tool will change these values. And then I'm just dividing these these sections into two different components because I just want to rotate this small sections profile. That's why I just divided this one, and with this rotate 3D component, I'm able to rotate these objects about their centroid. And then again, I'm combining these profiles and creating this bounding box, which will give me the panel area from which I can fabricate these profiles. And in here, I would like to show you something. I deconstructed this bounding box. And if you deconstruct, then it will give you the X, Y, and Z plane, which is in the domain. So it's from 1.22 to 7.12. But if you want to get the actual length or actual value of this X dimension and the Y dimension, then if you just directly use this number component, it will give you the value instead of giving the domain. If you can compare this one, this is 5.9. And in here in the Rhino viewport, it is 5.9. So it's just a small tip. If you want to convert your domain into number, just use this number component. And in here, I'm just making these dimensions in the Rhino viewport using this align dimension component. There is an alternative way to create this weighted average fitness function, and you can do it by using a weighted average component. You can connect the fitness value to this weighted average input, and then you can define the weight factors by connecting the same amount of number of sliders, or you can use the gene pool as I have used here. And then you can use this arithmetic mean as a fitness for Galapagos. So this is an alternative way to create this weighted average, which I have done here. So now let's move to this Galapagos tool, and let's open this one. In this one, I want to minimize the fitness function. First, I will show you the genome which I have used. So I have used these three genomes, this X direction, Y direction movement, and this rotation. So these are the parameters which will be changed during the optimization. And then my fitness function is this one. For this one, I'm using this combined fitness function, which I have defined earlier. Now let's open the Galapagos and check the solvers. First, this is the fitness. In our case, we want to minimize the fitness. So we will select the minimize. Otherwise, there is the option of maximize if you want to maximize it. So Galapagos has two types of optimization algorithms. The first one is evolutionary, and the second one is annealing, this one. And generally speaking, it is advised to use this evolutionary solver because it searches for good result and then it optimizes it, making small changes. But if in your workflow you have many or great degree of freedoms, then it is expected that it may lead to bad results in case of evolutionary solver. So therefore, it is advised to use this annealing solver. You can check by choosing first evolutionary and the annealing, and by changing these parameters, you can check which one will give you the best optimized solution for your workflow or for your target problem. Then let's keep the setting as it is. In this one, if you want to increase this initial boost, you have the option. You can choose between 1, 2, 5, 10, 20, and 50. It depends how much and how many degree of freedoms you have in your workflow. So let's start our first solver, this evolutionary. And if you want to see each and every iteration, you should select this option. It will show you the each and every iteration in the Rhino viewport. But it takes a lot of time and a lot of memory, so it's better and it's advised not to use this one. But I want to show you, let me use this one and let's see. In the Rhino viewport, you can see these objects started moving and arranging. And if I show you the sliders, you can see that these sliders are changing. And according to these sliders, the objects are moving in the Rhino viewport. And if you run this one, and here also you can see these clashes. When you have a clash, then you will find 1 here. If there is no clash, then there will be 0. So there are some clashes, and then they moves away, and then again. So if you keep running this solver for few more iterations, you will get to the optimal solution. And let me stop this one. And let's try the other one. So in the other one, it's the same. And you can see that the objects are started moving, and it's a bit faster than the evolutionary in this case, that it's arranged the objects like very quickly here. And if you want to go to another solution or another iteration, you can just press this button, and it will skip this one and move on to the next one. And you can see here, it started arranging the objects again with new solution. So that's how you can optimize your panel packing or your fabrication process. And in the same way, you can reduce your material wastage. You will find this value here. And you can also use, you can connect this fitness function to this arithmetic mean. And you can also connect here your material wastage fitness also. And then you can try to check which one give you the best solution. So it always depends on your initial inputs, even the ranges of these gene pools also, and it affects your optimization. So that's how you can perform the optimization using Galapagos component, which is the native component of Grasshopper.